So, what if I told you that the secret to escaping a massive, mind-numbing traffic jam or, even solving global water scarcity is actually to slow down the cars entering the highway?
I mean, it sounds completely backward, doesn't it?
Right. But today, we are looking at the terrifying hidden math of exponential growth
Hmm.
and why almost everything we assume about fixing our biggest problems is just, well, it's completely backward.
Yeah, we are basically trying to answer one massive question for you today. When you combine exponential human growth with finite earthly resources, does that equation equal a glorious boom or an absolute devastating bust?
All right. And it really is the ultimate reality check for modern society, I think.
Oh, absolutely. Because whether we're talking about global supply chains or just, our own personal schedules, we operate every single day as if that equation is perfectly balanced.
Yeah, or at least we act like we have plenty of time to figure out the math before the raw materials, the capital, or the energy just completely runs out.
Exactly.
Yeah.
We assume there's always a buffer.
Okay, let's unpack this. Because I know terms like macroeconomics and theory of constraints sound incredibly dense, like something reserved for an MBA textbook.
Yeah, it can be a bit dry.
Right, but this is actually about the invisible architecture of your everyday life. So our grounding source for this deep dive is a presentation by Dr. Alan Barnard. And the origin story of his research is just fascinating.
It really is.
The UN Development Program actually approached him with this massive, audacious question. They wanted to know if the theory of constraints, which, is a methodology usually used to make factory floors run smoother, if that could be scaled up to solve macroeconomic global problems.
Yeah, they were essentially asking, can factory logic solve world hunger and global poverty?
Which is such a brilliant, unconventional leap to make.
It totally is, because the theory of constraints, or TOC, is fundamentally about finding the single bottleneck in any system and relentlessly managing it. And the UN recognized that, sure, using TOC to help corporations increase their profit margins is fine. But applying those exact same mathematical principles to global resource scarcity.
That could actually move the needle for humanity's survival.
Exactly. And Dr. Barnard anchors his entire thesis in this great quote from Ellie Goldratt, the physicist who actually created TOC. He said, "Facts don't cease to exist because they are being ignored."
Wow. Yeah, that hits hard.
It does. And today we're looking at counterintuitive facts about system capacity that most people, corporate boards and governments, are just aggressively ignoring.
So to really grasp how a factory bottleneck relates to global survival, we have to look at the historical promise we've all been sold.
Right, the post-war vision.
Yeah. Leaders like Nelson Mandela and Harry Truman built this whole vision of a better life for all. But when you look at the news today, whether it's rolling blackouts in South Africa, global supply chain collapses, housing crises, we are clashing hard with reality.
Yeah, the exponential growth in our population and consumption is basically slamming headfirst into a wall of finite resources.
And this is where we have to categorize the problem correctly, right? Because not all scarcity is created equal.
Precisely. Dr. Barnard explains there's a crucial difference between the two types of scarcity we face. So the first type is temporary scarcity.
Okay.
This is a bottleneck that delivers a sudden, painful shock to the system like, say, a major shipping canal getting blocked.
Right. We've all seen that happen.
Yeah. You see early warnings, it hurts the economy, but humanity is incredibly adaptive. You can ultimately find a workaround, and the system recovers.
But temporary scarcity isn't what keeps economists awake at night, is it?
No, not at all. It's the second type. Finite scarcity. This is the oil, the arable land, the fresh aquifers.
The stuff that just runs out.
Exactly. With finite resources, there is no permanent workaround using the current model. The only real way out is to figure out how to squeeze significantly more efficiency out of the system you currently have.
Just to buy humanity enough time to invent or discover a totally new alternative.
Yes, exactly. Because if you don't buy that runway of time, the consequences are catastrophic.
Now, here is where I want to push back a little on the panic.
Right.
Because as someone just going about my day, I feel like we usually have a reasonable amount of warning before a massive system completely breaks down.
You'd think so, wouldn't you?
Yeah. Think about it like the fuel gauge on your car. You start a road trip with a full tank of a finite resource gasoline.
Okay.
And as you drive, that needle slowly, predictably ticks down from F to E. You have miles and miles of linear warning to realize, oh, I need to pull over and find a gas station. We can clearly see our resources depleting, so why the sudden catastrophic crash?
What's fascinating here is that your fuel gauge analogy perfectly illustrates our biggest collective blind spot.
Wait, really? How so?
The assumption that we have more time is the fatal flaw in how the human brain perceives exponential growth. We look at a historical trend, and for a very long time, it appears completely linear.
Like the needle on the dashboard.
Right. The depletion of a global resource looks manageable, but exponential growth doesn't behave like a static fuel tank. It appears flat and manageable right up until a sudden, aggressive turning point.
Oh, I see.
It's a cliff edge. And at that edge, the math violently changes, and the system goes from stable to complete chaos almost overnight.
But waiting until you hit that vertical wall means you're already going over the cliff.
Exactly.
So how does that sudden collapse actually play out in the physical world? There's a mathematical rule for this in the research, right? Queuing theory.
Yes. Queuing theory is basically the mathematical study of waiting in lines. And what the data definitively proves is that as the arrival rate of something, whether that's cars trying to get onto a highway or raw materials entering a supply chain, as that rate starts approaching the maximum capacity of the system, the queues do not grow linearly. They grow exponentially.
Oh, wow. I actually see this every single day on my commute.
I'm sure you do.
Yeah, when the highway is at, say, 50% capacity, an extra 100 cars merging doesn't change my speed at all. I don't even notice them.
Right.
But when that highway hits 90% capacity, just 10 extra cars merging causes this shockwave of braking that backs up traffic for 3 miles.
Yes. That is the exponential queue in action. And on a macro level, we see this in poverty, in unemployment, in administrative backlogs.
And here is the truly dangerous compounding factor from the research. As those exponential queues grow, the reliability of the service being provided decays exponentially as well.
Which triggers a vicious psychological cycle.
Exactly. Let's say you're a manufacturer and you order critical parts from a global supplier. Their system hits that 90% capacity mark, the queue explodes, and suddenly you only receive half of the parts you desperately need.
So what is your immediate reaction?
Oh, I don't just sit there. I panic. If I know they're only going to fulfill half my order, the logical move is to order double what I actually need next month. Just to guarantee I get enough to keep my own doors open.
Precisely. And by panicking and ordering double, you and thousands of other customers have just thrown massive artificial demand onto a system that was already cracking.
So we actively accelerate the collapse.
You do. Look at what happened to this Toyota supplier mentioned in the research. It perfectly highlights how sensitive that tipping point is.
Oh, this story is wild.
It is. So this supplier was a rock star. For 5 solid years, they had a perfect 100% due date performance. Their lead time was 4 weeks, incredibly reliable.
Right.
Then one of their marketing directors goes overseas and manages to secure just a tiny bit of extra business. They added a mere 5% increase in demand to the factory floor.
A 5% bump. I mean, if we think linearly like the fuel gauge, you would assume their lead times might increase by 5%, maybe a day or two longer.
Right, that's what anyone would guess. But within 3 months of adding that tiny 5% demand, their lead time skyrocketed from 4 weeks to 12 weeks.
It tripled.
It tripled. They crossed that invisible exponential boundary somewhere around that 80 to 90% utilization mark, and the queue just erupted.
But the theory of constraints offers an immediate, though deeply counterintuitive, fix for this, right?
It does. When you hit that crisis, you don't immediately start building a new factory.
Which is what everyone wants to do.
Exactly. But you do the opposite. You choke the release. You intentionally throttle the new orders going into the system.
So you bring it back into a state of stability by pulling it back from the cliff edge of that 90% capacity mark.
Yes, you don't need a massive $1 million improvement in efficiency to reverse the damage. You just need a slight reduction in the initial release of work to let the physical queue on the factory floor clear out.
Okay, but if a tiny 5% bump can ruin a company's lead times, how are leaders supposed to spot this disaster before lead times triple? Because once you're at 12 weeks, you've already lost your customer.
That's the $1 million question.
But there is a way to visualize this early warning system using Little's Law and cumulative flow diagrams.
Yes, these diagrams are brilliant tools. You basically graph out cumulative demand, the total orders coming in over time, as one line, and then you graph cumulative supply, the total shipments successfully going out, as another line underneath it.
Okay, I'm picturing it.
The vertical gap between those two lines at any given moment represents your current lead time and your work-in-progress inventory.
And Little's law reveals a terrifying mathematical truth about the relationship between those lines.
It really does.
If you have a once-off increase in demand or a once-off disruption in your supply chain, say, a port shuts down for just 1 week due to a strike,
Right.
your lead time will permanently extend forever, unless you have excess idle capacity sitting around to run double time and catch up.
Which nobody has these days.
Exactly. If your system is already running at maximum capacity, that one-time delay becomes a permanent baked-in feature of your reality.
It is a brutal mathematical reality that most managers just refuse to accept. We have this optimistic assumption that systems naturally self-correct over time.
But they don't.
They don't. Without excess capacity to absorb the shock, the gap between demand and supply never closes. But where it gets truly disastrous is when demand is continuously growing and supply is growing at a slower rate, or plateauing.
When the demand line completely crosses over the supply line.
Exactly. When that happens, it's game over.
The iPad example from Dr. Barnard's research completely blew my mind on this front. We all remember the absolute frenzy to get the early iPads.
Oh, lines around the block.
Right. Apple was selling them at a record-breaking rate. But because consumer demand continuously crossed the supply line, meaning demand wildly outstripped Apple's forecast, which was matched to their factory capacity, the system broke.
It did.
The research estimates that Apple permanently lost around 25% of potential sales on both the iPad 1 and iPad 2 simply due to unavailability. People got tired of the exponential queues and just gave up waiting.
A quarter of total potential sales vaporized into thin air. And not because the product was inferior or because marketing failed.
No.
It was because they couldn't react fast enough to the mathematical certainty of those lines crossing.
Here's where it gets really interesting, though. It's not just about missing out on selling consumer tech. Dr. Barnard notes that Ellie Goldratt actually mapped this exact same cumulative flow diagram onto national healthcare.
Yes, the stakes get much higher.
What happens when the demand for health services crosses the budget and capacity available to provide them? It's the exact same math as the iPad factory. The line crosses, the queues go exponential, the reliability decays, and the system breaks.
And the tragedy here is that we have these early warning systems. The flow diagrams are right there.
But we ignore them.
We ignore them because we rely on a fundamental misconception. We assume we can just manage our way out of the math through sheer effort and late nights.
Which leads us to a structural question. Why does our supply always seem to fall short of our expected capacity in the first place?
Right.
If a hospital administrator or a factory manager calculates that they can process 10,000 units a day, why do they rarely hit that number consistently?
It's a great question. Because we build infrastructure for a specific capacity, and our forecasting software promises us a specific output.
Why can't we just mathematically produce what we forecast?
To explain this, the research introduces this incredible simulation called the dice game. Have you ever seen this played out?
I read about it in the source material, and it's fascinating.
The dice game is designed to expose two invisible forces that absolutely ruin our forecasts: interdependency and statistical fluctuations.
Oh, okay.
So imagine a production line with 5 distinct workstations in a row, A, B, C, D, and E. To simulate daily production, the worker at each station rolls a standard 6-sided die.
Right.
The number they roll represents the amount of work they successfully processed that day.
Okay, so a standard die averages 3.5 over time. So each station can process an average of 3.5 units a day. If we run this simulated factory for 20 days, logic says we should take 3.5, multiply it by 20, and get a total output of 70 units. That is exactly what our forecasting software would report to the shareholders. Expect 70 units this month.
But when you actually sit down and play this game with real people rolling real dice, passing the work from one station to the next, the final output at Station E is never 70.
Never.
Never. It almost always lands somewhere between 30 and 40 units. Your actual average output is only 1.5 to 2 units per day. You lose roughly half of your promised capacity just by playing the game.
Wait, I think I see exactly why this fails, and it has to do with how the stations are chained together.
Go on.
If I'm Station A and I process 1 unit and hand it to Station B, now the person at Station B rolls a brilliant 6. They have the energy and capacity to do 6 units of work today.
But
they only have 1 unit sitting in front of them from me. I've starved them.
Exactly. They waste 5 units of potential capacity because you, the previous station, had a statistically bad day.
This is exactly like my office workflow.
I'm sure everyone listening can relate to this.
It's like when I finish my part of a massive project in a single afternoon, I rolled a 6. But then I email it to the legal department and it sits in their inbox for 2 weeks because they are understaffed and rolled a 1.
Yep.
My speed didn't matter at all. The math assumes we are all acting independently, but we're shackled together.
That is the perfect real-world parallel. You experience starvation and blockage. In an interdependent system, a statistical fluctuation on the high end rolling a 6 cannot be fully utilized because you are limited by the input from the person before you.
Right.
But a fluctuation on the low end rolling a 1 propagates like a shockwave through the entire system. The slowest station on any given day completely dictates the whole system's output.
So the concept of independent averages is just a myth when things are connected.
Exactly. The mathematical average output of an interdependent system will always be significantly less than the average capacity of its bottleneck.
That is incredibly daunting. Statistical fluctuations naturally drag any interconnected system down by half.
Yeah, they do.
So if I'm a factory manager or a hospital administrator running the system, my first instinct is going to be, I need millions of dollars to buy better machines, hire more lawyers, and stop my team from ever rolling 1s.
And that is exactly the trap most leaders fall into. When managers play this dice game and realize they're only producing 35 units instead of 70, they try to fix it without a budget by adding inventory buffers.
Okay, how does that work?
They put a Kanban buffer, which is basically just a small designated pile of backup inventory between every single step in the chain, a little safety cushion of 1 unit everywhere.
Which, according to the data, does help a little. The throughput bumps up to about 40 or 45 units.
It's better, but it's still nowhere near the promised 70.
Because spreading thin inventory buffers everywhere doesn't solve the core mechanical gridlock.
No, it doesn't.
Here is the genius, highly counterintuitive solution from the theory of constraints. It involves 2 steps. Step 1, take all those little Kanban buffers spread across the system, group them together into a single larger buffer of 4 units, and place it solely in front of the bottleneck.
Let's say resource C is our bottleneck. You put the whole pile of backup inventory right there to protect it.
Okay, that makes logical sense. You ensure the slowest component in the system always has material to work on so they never sit idle and are never starved.
Right.
But it's step 2 that completely goes against everything we were taught about productivity. Step 2 is slow down resource C. You intentionally reduce the maximum capacity of your bottleneck.
Yes.
In the dice game, you literally remove the 6ths from their die. Their average maximum capacity drops from 3.5 down to 3. So what does this all mean?
I know, it sounds crazy.
You reduce the maximum potential capacity of your slowest machine, and the whole system suddenly produces more. I'm looking at this thinking, wait, you intentionally handicap the bottleneck and you get more total output? Mechanically, how is that possible?
It comes down to the physical reality of what happens when a system is out of sync. When a fast, non-bottleneck station rolls a 6, but your bottleneck can only handle 3, where do those extra 3 units go?
They don't just disappear.
Exactly, they pile up on the factory floor. That growing mountain of work in progress, or WIP, causes physical and administrative gridlock.
Oh, I see.
It hides manufacturing defects until it's too late, it eats up operating capital, and it forces workers to constantly navigate around piles of half-finished goods.
So by removing the 6, by intentionally slowing the machine down to a steady, predictable pace, you prevent the gridlock.
You do. You completely eliminate starvation for your bottleneck, and you stop the chaotic pileups. When teams do this in the dice game, throughput skyrockets to nearly 60 units.
You literally design the chaos out of the system.
Yes.
And if we pull this all the way back to the UN's macroeconomic premise, this is exactly how factory logic solves global problems.
Bingo.
If we stop flooding global supply chains, whether that's shipping lanes, agricultural fertilizer, or capital deployment, with chaotic overproduction and panic ordering, we stabilize the entire global flow.
We actually get more output with the finite resources we already have.
And that increased efficiency is what buys humanity the time needed to invent alternatives. Yeah.
Exactly. You stabilize the flow to buy the time. And it's worth noting, this exact same mathematical logic applies to something we all do daily: bad multitasking.
Oh, don't get me started on multitasking.
When we constantly switch between 5 different open projects, we mistakenly think the only thing we're losing is setup time. The few minutes it takes our brain to refocus.
Right.
But in reality, we are losing the synchronization of our whole workflow. We are creating massive starvation, blockage, and WIP gridlock in our own minds.
We are artificially creating temporary scarcity in our own lives by refusing to stabilize our inputs.
Exactly.
Whether it's a massive global supply chain, an iPad factory trying to meet consumer demand, or, your own daily task list, the principle is identical. You cannot outwork chaotic fluctuation.
You really can't.
You cannot just hustle your way out of exponential queuing.
No, the math will always win.
So, to synthesize all of this for you listening,
Yeah.
whether we are staring down the barrel of global resource depletion, sitting in a mind-numbing traffic jam, or trying to figure out why a company's production line is failing to meet forecasts.
The answers are rarely just build more capacity or work longer hours.
Right. Sometimes the most brilliant, effective move is spotting those exponential cues early. It's about finding the critical bottleneck in your system, fiercely protecting it with a targeted buffer, and intentionally slowing down the chaotic inputs so the entire system can actually speed up.
If we connect this to the bigger picture, back to that promise of a better life for all that leaders envisioned decades ago, we actually have the mathematical tools to achieve it.
We do.
The theory of constraints proves that we don't necessarily need infinite resources to survive exponential growth. What we need is immense discipline.
Yeah.
We need to stop pretending that complex systems have infinite elasticity, and we need to stop ignoring the early warning signs of flow diagrams just because the data is politically or financially inconvenient.
It really is a totally different paradigm for viewing the world, and I want to leave you with a final thought to mull over today.
Okay.
We've talked a lot about physical constraints here. Things like oil, capital, shipping containers, and tech gadgets. But what if the ultimate finite resource in your life right now is your own attention?
Oh, that's a great point.
Think about your daily schedule as that interdependent dice game. Are you constantly starving and blocking your own brain by trying to operate at maximum capacity every single hour of the day?
Most of us are.
Are you rolling a chaotic 6 on Tuesday, burning yourself out, and then rolling a 1 on Wednesday, completely ruining the rest of your week's workflow?
It happens all the time.
Maybe it's time to stop trying to add more hours to your day. Maybe it's time to group your buffers, protect your deep work, and intentionally slow down your own bottlenecks so you can actually get more done. Next time you look at that massive equation of your life's demands versus your finite energy, remember, you don't need to break the equation, you just need to change the math.